Okay.
Okay. Recording has been started.
So Parthada, please switch off your mic. Yeah,
Sure.
mute it. Yeah.
Hi, I am Anwesh. Thank you for the kind introduction and the kind invitation. So, what I will be talking today is mostly basics of optical astronomical telescopes and some related systems. Most likely, the systems part will have to wait for tomorrow, but we can just talk about basics of astronomical telescopes. The thing is, I don't want to go into too much detail, but at the same time, I don't want to simplify things too much. So let me start, and if something is becoming too complex, you can stop me at any time and ask for clarifications. So this was the list I gave. I'm hoping that I'll be able to cover most of these. So before we start, we have to be familiar with some unit conversion, particularly because we are talking of telescopes in the astronomical sense. The first thing is, well, we know a degree is 60 arc minutes, and one arc minute is 60 arc seconds. Most astronomical objects, let's say stars, will be about 1 or 2 arc second if you are observing them from the ground. Um, so that is the typical resolution we are aiming at. So the arc second is a benchmark for what the resolution of a telescope should be. The second is, well, 1 degree is 60 arc minutes and 1 arc minute is 60 arc seconds. So 1 degree is 3600 arc seconds. Then finally, one of the most fundamental conversions that we'll be using multiple times is the conversion from radian to arc seconds. The radian is a fundamental mathematical, we'll see that the any trigonometric function, if you don't do any conversion, the unit should be in radians, and 1 radian is 180 by pi degrees, and well, if you, so it's like 57 point something something degrees, and you multiply 3600, then this conversion factor comes around 206,265, actually like 64.8 something, but this is a reasonable conversion factor. We'll be encountering this number multiple times. So let's start with, what does a telescope do? So,
I'm sorry to interrupt. Anvesh, are you presenting? We are not being able to see this anything on the screen.
oh, wait, is it?
Entire screen, we choose the entire screen mode, present screen, entire screen. Now this click this, and then share. Hide. This one. And now it is present. Yes.
Okay, okay. I think it was not coming up. So I'll just flash this slide once again. It was just about units and conversions, and the most important one that will keep coming back to is radian to arc seconds. That's about this number. The next is, we'll talk about what does a telescope do in very fundamental terms. The first thing it does, it collects more light than you can do with a human eye. The second thing it does is provides resolution and magnification. Those things kind of go hand in hand. And the third thing that is more important for professional astronomy, or nowadays even for amateur or entry level astronomy, is some amount of instrumentation has to be included with the telescope. And that gives you some amount of objectivity and scientific validity to the observation. Anyway, so I have a picture here. It's not my picture, it's from YouTube, and it shows three sets of images. The first with naked eye, this is like typically what you would see the sky on a reasonably clear sky and low light pollution. If you use a binocular, you will see a little bit better, but not that much better. And then the right side, you see images of Saturn, and one of these things is the Saturn. I think it's the brighter source right here, but it's not very clear with a binocular. But on a telescope, depending on the telescope, you can see either image on the top or the bottom. Both of these are ground based images, so They're still not as clear as they could be, but they're definitely impressive. And finally, like this is on the right, on this side of the image we are looking at a Hubble field. The left side is the Hubble image and the right side is the JWST image. You can see there is some amount of improvement in resolution as well as light gather. But again, there is one more critical difference in between these two images, is that the left side image is a visible image and the right side image is an infrared image, so it can peer a little bit deeper into what we are observing. We'll come back to maybe a little bit on infrared observations maybe tomorrow. But again, these are the things that a telescope gives you. It gives you more light gather, it gives you more resolution, and then it also allows you a place to keep your instrumentation. And let's go very quickly go through the history of telescope. On the left we have actually two of the telescopes that were used by Galileo, and these have been preserved in the Max Planck Institute. And you can see how simple they were. They were basically two lenses and a tube, that's all. And on the right, this one is the extremely large telescope that is coming up in Chile. I think right now they are in primary mirror fabrication stage or something like that. And this is probably the largest telescope, at least visible telescope, that mankind is going to build in this century. And it's about 38 meters diameter, and you can see that it's a crazy thing. Um, but what I want to mention is that, well, we started with refractors with simple eyepieces like the Galileo's telescope. Somewhere in between, we actually moved to Newtonian telescopes with prime focus and with photographic plates as instruments. And then finally, we have this modern RC design. We'll talk about what an RC design is, and with CCD cameras. So, but at the same time, I will also like to impress you that it's not that refractors have gone out of business. They are still there. And in fact, the refractors that you can buy today are much better than what Galileo had. Similarly, you can buy much better Newtonian telescopes today than what was available in actually Newton's time. So there has been tremendous progress in the quality of telescopes available to astronomers in all types of telescopes. So let's jump straight into the some optics. This is, I think, some people might be familiar with this equation. It's called the thin lens equation. It basically gives you a relation between object and image, assuming we have an optics system that we can approximate to a thin lens. And the property of the lens is the focal length, and the lens is mostly defined by its focal length, and the relationship is like this: 1 over object plus 1 over image is equal to 1 over focal length. I think there is a slightly different version of this formula where the plus sign is replaced with a minus sign and you use a Cartesian coordinate system. But this particular convention assumes object and image distances are positive when object and images are real. And same for the focal length. If it's a converging optics, then the focal length is positive, otherwise it's negative. But again, without all of this, what we want to do is we want to simplify this equation for astronomical use. So first thing, well, what is the object distance in astronomy? The object distance in astronomy is always infinity. Well, most astronomical objects are so far from us that the compared to the focal length, which could be maybe 10 meters, a meter, maybe even 30 or 40 meters, the object distance is much larger. So the 1 over O term, it vanishes. So 1 over roughly infinity, it vanishes. So the image, 1 over image is equal to 1 over a focal length. So the image is exactly equal to your focal length. And well, so always your astronomical image is formed at the focal length, at the focus of your optics. There is no, you don't need to do any calculation. It's always going to be at the focus point. You don't need to do any extra optics or on the thin lens equation, because well, we know it's going to be there. And your since our object distance is going to be infinite compared to our focal length. So let's talk about the simple ideal telescope. It's a single optical element, but it's an approximation of a telescope. We'll talk about how to get from a real telescope to this approximation a little bit later. And it has only two properties. It has a diameter and it has a focal length. The diameter decides how much light we are collecting, And the focal length decides, well, the magnification and the um, size of the image that we are forming. These are only the two parameters we need to know. And well, of course, it's an ideal approximation. We'll find that there will be some deviations from this in real telescopes, but this is a good enough approximation to get started. Okay. Before we do further, there is a some semantic issue that we must address, is that in Galileo's time, the telescope had to include an objective as well as an eyepiece. So the objective, what it does is it focuses the object from infinity and it puts it at the focus. The eyepiece, what it does, it takes that focused image and then puts it back into a collimated state. So what it basically doing is it had a much larger diameter and it compressed it to a much smaller size. And this size is usually fixed to around 7 or 8 millimeters. That is the size of the human pupil. So, so basically, what this entire thing is doing is it's acting as a beam compressor. But most modern telescope, the eyepiece is not considered as part of the telescope because, well, most of the time, what you will do is you will put a CCD at the focus. So the telescope is now only considered as the objective lens. Again, this is a slight difference between the astronomical telescope and, like, say, a ground based telescope or like a laboratory telescope. But again, you will find people using the term interchangeably, so you have to gaze from the context what they are talking about. So let's we had two parameters of the telescope. One was the focal length, one was the diameter. Well, frankly, most people don't talk about the focal length of the telescope directly. What they do is they define a term called the f number. That is basically the focal length divided by diameter. Let's say we had a 1 meter telescope and it had a 10 meter focal length. Then the f number is, well, 10 by 1, it's f10. Usually, what you write when you write f number, you write, instead of this number, you will write 10. So the output of this telescope is called an f10 output. Similarly, you could have an f3, f5, f15 output. So then the number at the end, that's your f number. So this is a very simple way of defining the focal length. This actually only works for telescope. It doesn't work for cameras directly, because in cameras you can have things called iris apertures. Basically, what you can have is you can have one of these iris apertures, and you can place it in front of your prime, your objective or your light gathering aperture, and then you can reduce the aperture. Let's say you had started with a 1 meter telescope and you put a 1 meter iris and you squeezed it till it was only 50 centimeter. Then what happens? Your focal length is now 10 meter divided by 50 centimeters. So then now the f number is f20. Well, of course, you wouldn't do this in a actual telescope. If you made a 1 meter telescope, you would want to use the whole 1 meter of the telescope. But again, this is something to keep in mind. Again, when you are comparing astronomical instrumentations to, let's say, a commercial camera. Okay, this is the most important part that I will be talking about today. That is how to extract things like field of view and plate scale from just the focal length. Let's say we have this similar, we have a telescope. It's shown in the paraxial format, and we have two images, one on the axis, and then another bundle of rays coming from off axis, and they are focusing at a distance L, uh, from the center. So what we are trying to do is, we'll go back to this image, and let's say we have the blue rays. These are called the on axis rays, and they are coming from an object that is located at the center of your field of view. And then the green rays are coming from an object that has some angle to the center. So let's say an angle theta. All these green rays are at an angle theta to the blue rays, and then the green rays are focused on somewhere on the image plane. We would like to find out what is the distance between the blue focus and the green focus. Well, first thing we want to figure out is what is the we don't want to work with all of these rays. Let's take just the central ray for both the blue bundle and the green bundle. How do we know that the angle doesn't change between the central ray and the and the uh, central, let's say, the blue rays and the green rays? Let's look at it. Let's say the actually this one is supposed to be blue, the central axis, but it's black here. um let's okay, look at the how much each ray is being deviated compared to the height with which it comes and meets the aperture. You will see that the rays that are at the very high at the extreme edge, they get bent a lot because they have to come and meet at the center, and the ray that is exactly at the center, it doesn't get deviated at all. So we'll take this blue ray that is at the center of the bundles, and this green ray that is also at the center of the bundle, and these two rays do not get deviated by the optical system. They pass through the entire optical chain undeviated. So we can use these for a simpler calculation. You could do this calculation with any random height, but then you have to um, use the refraction formula, and the calculation becomes a bit messy. On these central rays, since they go undeviated, the calculation is much simpler. Okay, so we have a ray that is going along the center on the so at the center of your field of view, and then it is coming at an angle theta. And well, we know that both of them land on the image plane. So, and the only relation that you can find between the image height and the focal length is that the image height is L equals to F tan theta. So it's a very simple relation, but usually we simplify it even further. We take the approximation of tan theta equals to sine theta when theta is very, very small. And yes, in astronomy, our field of view is going to be 1 degree at the most. So it's a reasonable approximation. So your theta is equals to L over F. But we don't want this format where theta is equal to L over F. We want to express it in theta over L. So what is theta over L? Well, we know it's called your plate scale. For a certain field of view, what is the size of your image? And usually if you don't do anything, theta over L, it's that will come out in radians per millimeter. So theta is an angle, its unit in, if you don't do anything, its unit is radians, and L is a distance, so it's radians per millimeter. But radians per millimeter is a very unwieldy formula to use. So what you do is you use the radians to arc second conversion, and that conversion factor, if you remember, is this value 206265. So then the plate scale equation simply becomes 206265 divided by your focal length. And if you don't know the focal length, you only know the diameter of the telescope and the f number, then this formula simplifies to something like this. And we'll use this formula. We'll try to get acquainted with this formula a little bit. Let's talk about what this does, what this means. Let's say you have a short focal length system and a long focal length system, and you have a sensor or a detector size that is fixed. You cannot get a bigger detector. The detector size is fixed. So what happens is that for the shorter focal length system, you have this image height is matched by a fairly large field of view. On a longer focal length system, this image height is reached by a very small angle field of view. So what happens is that on the longer focal length lens, you have bigger magnification because a small angle is now magnified to a very large linear distance. But on the shorter focal length system is useful because if you want a very large amount of angle of sky and you want to match it to a smaller detector, then you want a shorter focal length lens. But if you want to have more magnification, let's say you have take a small area on sky and you want to blow it out so that it covers much bigger area on the detector, then you want longer focal length lens. What I will do is I will go through some simple solved examples just to make you familiar with this technique or whatever, just make you familiar with the process. Let's say we have a Celestron CGX 7-inch something telescope, and we know that this thing has an output of f15. The question is, can we calculate its focal length? Yes, of course we can. And if we were to attach a particular camera, this time I have selected a Raspberry Pi HQ camera. It's a very cheap camera, and it can be interfaced fairly easily because it's software and everything is open source. So let's see if we can solve this problem. So I'll just open the document. Okay. So this is the problem. We have a Celestron 7-inch telescope and we have a camera. We want to match these two. Well, what is the diameter of the telescope? They say it's 7 inch, so 7 inch is about this many millimeters. It has an f number of f15. So well, the focal length is d times f. So this is the focal length. We found the focal length, simple enough. And the plate scale is 206265 divided by the focal length. So and then it, because we have used this one in millimeters, we'll get our output in arc seconds per millimeter. So this thing is 77 something arc seconds per millimeter. Then we want to go and find out what is the size of the camera that we want to use. Well, you can go and find out the size of this camera. This camera sensor size is about 8 millimeter by 6 millimeter. I believe this is only a 2.5 micron size pixel, so it's a very good sensor because it will give you fairly good resolution. So well, we know that the camera size is 8 millimeter by 6 millimeter, and our plate scale is 77 arc seconds per millimeter. So well, if it is 77 arc seconds per millimeter, how much is it for 2 millimeters? Well, 77 times 2. And for 8 millimeter, it's, well, you multiply by 8 and then you get 619 arc seconds. And we, well, usually want to specify field of view in arc minutes. It's just a quirk of astronomy. We want to specify resolution in arc seconds, and usually people want to specify field of view in arc minutes. So 619 arc second becomes 10.3 arc minutes. Same for the shorter side of the sensor. It's a 6 millimeter sensor, so it comes to around 7.7 arc minutes. Okay, so this is problem one solved. Let's move to a slightly more difficult problem. The problem is about the Kodaikanal Tunnel Solar Telescope. It's a telescope I have visited when I was doing internship for IIA. And so the tunnel telescope is something, it looks something like this. It basically, it has a dome and it has two flat mirrors in the dome, and then it directs light to an underground tunnel where you have a single we have a doublet lens, and then the lens has a focus somewhere around. So the entire observatory is basically a tunnel that's horizontally placed. And if you see these white things here, these are vents, because just because it's an underground, it's going to get hot. So you want to have some amount of air ventilation here, and these things show you where the tunnel is headed. And if you see it in this picture, then the tunnel is actually pretty long. It's actually difficult to fit the entire thing in one picture, but again, it's about a we'll see how long the tunnel is when you solve this problem. So the tunnel telescope, it has an refractor lens. It's 38 centimeter doublet, and it has an f90 output. So we want to, and it's a solar telescope, so we want to see the sun. So let's calculate what is the size of the sun on this at the output of this telescope. And it's actually used for spectroscopy after the image plane. And let's say we want to have 1 arc second resolution on the sun, then we can think about what size of slit we should be using. Okay, so let me go to the other document. So okay, so we know the size of the main light gathering element. So in this case, it's not a reflective telescope, it's a refractive telescope. So so f number of f90, so it's a very slow telescope. So and then what you do is you multiply the diameter with f90, so then you get the focal length. The focal length is here coming around 34,200 millimeters, so about 34 meters. So you know that that tunnel has to be at least 34 meters. Well, the tunnel actually is 34 plus 20 meters because it has to accommodate the spectrograph also. But um, that is the size of the tunnel we're talking about. So the focal length is 34 meters. We can calculate the plate scale. The plate scale is 206265 divided by the focal length. And then this time it gives us a very small number because we had a very large focal length. So then the plate scale is 6.03 arc seconds per millimeter. Well, what is the typical size of the sun? That's what we want to image on with this telescope. The size of the sun is about 0.53 degrees, half a degree. It changes a little bit, but it's about 0.53 degrees. We can start with this number. And then in how much is it in arc seconds? 0.53 into 3600, that gives you about 1908 uh, 1908 arc seconds. So well, we have the size, we have the field of view, and we have the plate scale. If 6 arc seconds take up a millimeter, how many millimeters do you need to fit 1908 arc seconds? Well, you just divide 1908 divided by 6.03. That gives you a size of around 316.4. So the size of the output image of that telescope is about 30 centimeters big. It's a pretty bright output, and because it's the sun. And well, we're not done here. We want to know what size of slit we should use that should correspond to 1 arc second on the sun. So 1 arc second is the typically minimum resolution that we can resolve with these kind of telescopes. So and we want to take spectra of some feature on sun that is only 1 arc second. So well, we know 6.03 arc seconds is 1 millimeter. Then 1 arc second will be, well, about this many millimeters, 0.16 millimeters, or like 160 150 microns. So that's the typical slit size you need to make this spectrograph work. Okay. So, and I have one more solved problem. This might get a little bit repetitive, but I think it's good to go through it. So let's say we have a 3.6 meter diameter telescope, and we have a fixed CCD. We know that the CCD is 4000 by 4000 pixels, and the pixel size is 15 microns. And we know that the telescope output is f9. Well, what is the field of view if we use this detector on this telescope? And well, I'm asking for one more thing. What is the pixel scale? I was talking about plate scale, so that is arc seconds per millimeter. The pixel scale is arc seconds per 1 pixel, and depend on the pixel size it will change, but here we'll talk about a 15 micron pixel. And well, finally, we want to see if we want to image a 10 by 10 arc minute, so like 1/6 of a degree into 1/6 of a degree, then what should be the f number? The telescope comes with f9, but if we want to fit this 10 arc minute field of view, then what should have been the telescope f number? And well, maybe tomorrow we can talk about how do you change the output f number, but right now we'll just calculate this to find a number. Okay, I think okay. So okay, so well, again, we'll start in the very similar fashion. What is the diameter? It's 3.6 meters, so 3600 millimeters. What is the f number? It's at 9. So what is our focal length? It's diameter times f number again. And then, well, we find that this number is actually quite similar to the old tunnel telescope f focal length, but well, that's fine because one of them was around 10 1/10 of the diameter, but f number was f90. But that is fine. The focal length is around 32 meters. Well, what is the plate scale? Plate scale is 206265 divided by the focal length. So then again, we get a very similar plate scale, 6.37 arc seconds per millimeter. And well, that is the plate scale. How much, if you have 6 arc seconds per millimeter, then how many arc seconds do you have for a 15 micron pixel? Well, you just multiply 6.37 times 0.015, and then you get this arc seconds. So it's about 0.1 arc second pixel scale. And we know the size of the detector, it's a 4000 pixels and 15 microns. So the size of the detector is about 60 millimeters. So then field of view will be, well, around 6.3 arc minutes, because we use the again the plate scale formula. Now we want to do this calculation in reverse. So let's say we want 10 arc minutes. If we want 10 arc minutes on a 60 millimeter detector, then the plate scale must be 600 arc seconds divided by 60 millimeter. Then that is 10 arc seconds per millimeter. So then, well, we know the plate scale. Now we know the plate scale. It has to be 10 arc seconds per millimeter. But the plate scale is equal to, again, 10 arc seconds is equal to 206265 divided by the focal length. But now we don't know the focal length because we don't know what the output f number should be. But we can make this equation and then we can solve for f number. And well, you just take f number to the left and top, and 10 arc second drops down, and then the f number should have been 5.73. Yes. So if you had this telescope, put output a f number of 5.7, then it would have produced a 10 arc minute field of view on the given detector. So again, you can the point of showing these worked examples is when the next time you see a particular telescope or a particular camera, so you can do these calculations to figure out what field of view can be achieved, what kind of pixel scale can be achieved, and so what kind of astronomical sources that are of interest to you could be accessed from such a telescope and such a system. The reason we focus on plate scale is this is a link between science, optics, detector, and optomechanics and everything else. So this the plate scale decides the nature of the science. If you want a survey type instrument, then you want a lot of field of view. So you have to have a very short focal length system. The short focal length system will have its own challenges in very fast optics and some optomechanical challenges. The same with a very long focal length telescope also, because again if the thing becomes very long, you really don't know how to handle this. So, and again, for different science things, let's say if you want to do photometry or astrometry or astroseismology, these are all simple imaging based science cases. You would want different pixel scales. For survey, for if you're trying to do survey, you want a lot of field of view. So you don't want um, you don't want a very large magnification. So each pixel will actually sample a fair amount of sky. For photometry, astrometry, and astroseismology in this order, what you want is you want more and more magnification. So therefore your f number has to be higher and higher. For astroseismology system you might need some additional help. So again, so this shows that the pixel scale for photometric systems, it has to be smaller than a survey, and again smaller probably for an astrometric mission, and then again smaller for an astroseismology type observation. But so the reason we want to talk about plate scale is we did this equation and its derivation without looking at what the details of the telescope is, which is good because now what we have a relation that is universal. We don't have to worry about what telescope it is and what it is doing. We can just use this equation to link our science to the instrument. Now it will be the work of the optical designer to make sure that this particular f number and with this diameter is achieved. Okay, so we'll talk a little bit. So now we have talked very briefly about the plate scale part. Now we'll actually try to get a little bit into the optical design of uh, optical design basically. So the first thing we have to learn about it, and from now on it's going to be a bit more technical, because well I have to talk about optics, which is kind of complex and non-linear in so many ways. So but we'll start with this um, fundamental optical principle. That is, let's say we have some beam coming to a lens or optical system, and what we want to achieve is that we want to bring all of these rays into a focus, one single point focus. Well, this diagram looks a little bit blurred, but what we want is we want it all come to one point of focus. Then what criteria must we satisfy for in order for this to happen? The principle, it says that for this to happen, the path length between all of these rays must be the same. So what is it's not just the path length, it's the optical path length. Well, let's talk about the ray that is at the bottom here. You see that this ray is traveling, clearly it's traveling a longer distance in air. So clearly so how is this path length equal to the path length of the ray that is traveling at the center of the axis? Well, what we also see is that this ray is traveling a much shorter distance within the lens, where the refractive index is higher, and the ray at the center is traveling a much longer distance within glass, where the refractive index is higher. And uh, and the principle says that your refractive index multiplied by the path, and well the summation is for different segments. Here one segment would be from your object till the lens, the next segment would be the distance traveled within the lens, and the next segment is the
আরে মানে
distance
তুমি
traveled
এদের
from the
সঙ্গে পড়ছি
lens
এখন
to
ওই
the focus. So
শুভমদের সঙ্গে আচ্ছা তো
so
আগে
what we
মানে
want to do
বুঝতেছি না
is what we know is that
ওরা
if
তো
our
প্রথম থেকেই পড়ছে তো
optical system has to produce a focus, then it has to match this criteria.
আহ,
It's
তুই আমাকে
usually
একটা
there
কাজ
is a
করবি,
much more
নাম্বারে তুই
formal
আমাকে একটা
definition of it
হোয়াটসঅ্যাপ
when you
মেসেজ কর, আমি তোর
introduce
এটা
this
শুরু
in
করে
a
দিচ্ছি। আমাদের ক্লাসটা
optics
শুরু
class.
হবে
It's
কিন্তু
but
ফেব্রুয়ারি
again
মাস
we
থেকে।
will stick with the
তোর কি
slightly
নাম?
simpler description, but it is again the formal
আচ্ছা
description
আচ্ছা
basically instead of
আচ্ছা
segments you
যাদবপুরে তো আরেকজন জয়েন করেছে,
it's basically an
তোর
integral,
তোর
it's a
জুনিয়র আছে,
path
সে
integral.
তুই পাঠা,
But
আমি
again
তোকে
this
গ্রুপে
is
লিখে
fine.
দিচ্ছি, গ্রুপে জয়েন করে
Most
করে
optical
নিচ্ছি
system that
করবো।
will encounter will
ঠিক আছে,
not need path integration. It
হ্যাঁ
can
হ্যাঁ
be segmented into different
তোর
parts.
নামটা লিখে পাঠাবি একটু, ঠিক আছে?
Okay, so
ঠিক
then next we talk about the PSA. The let's say we have a system that is bringing all the rays into exactly focus. Then how do we quantify the nature of the well, how well it has done the. So the criteria for it, that is called the point spread function. It's called PSA. It's a measure of imaging quality, and this is the distribution at the image plane. If you have very good image, then the distribution is very high. is a vanishing point. There is no spread, so it's just a point, and that's the ideal case. But so this PSF is corresponding to the ray trace that we saw here, and you see that it's reasonably good. You might see some of these plots. It's called a spot diagram. It is basically used to display a PSF. The spot diagram is basically you have some x and y units, and it will show you the distribution of position locations where the rays landed in the image plane. And you will see that it's a 10 micron by 10 micron scale, and all the rays have landed very nicely inside of this system. So well, it's a very good system because it has focused everything under 10 microns. But we'll also see that as we get into real optical systems, the PSF is going to be bigger and bigger. In fact, uh, we'll see one right away. Okay, so we'll see this thing called spherical aberration. So we have a very similar system. It's only difference between this system and the previous system that we showed is that now this surface that I'm showing is actually spherical. The previous surface that I showed you here, this is not a spherical surface. This is a hyperbolic surface, and well, we'll talk about why it had to be hyperbola to bring all these rays to focus. Basically, if you solve this equation, then the equation for this surface has to be a hyperbola. But well, what if it is not a hyperbola? Because well, hyperbolas are difficult to produce in optical manufacturing. Spheres are much spheres are much easier. So well, what we do, so let's do this experiment with a real lens. Let's say we have a spherical surface. Then let's look at what happens at the image plane. Immediately you can notice that there is this definitely something wrong here. And well, if you zoom in, let's say to this region, you see a pattern that's almost like the tail of a fish. And well, what is happening here? Let's look at some of these rays from the extreme edge of the aperture, and you see that they're not staying in their lane. They're kind of cutting through all the other lenses, and then they're coming to focus much before where the actual focus point should be. And what happened is that the rays from the outer rings, they have decided that the focal length is not at this distance. They have decided that the focal length is here. And this is a result from the surface being spherical, and then so it cannot bring all of these rays into focus at one point. And so there is a disagreement between some aspect of the optical system as to where the focus point should be. And we'll see that this principle actually follows through for a lot of optical aberrations. Like the system cannot decide where exactly the focus point should be. So you have a, instead of one single focus point, you have multiple focus point, and then you have a much bigger point spread function. So here for the case of spherical aberration, uh, I think this thing is frozen.
Got frozen somehow. Some maybe in the
Yeah.
background some update or something is going on, so it probably. Okay, we are just returning back within 2 minutes. Somehow some system got frozen. We're just looking into the issue. Okay. Okay, 1 minute. Anesh, yeah, I guess audio is not audible.
Oh, this one is clear.
There. Now it will be audible. Yes, yes.
Okay. Hi. Okay. So,
Yeah, the previous slide. Yeah, once.
yeah. So I'll start again a little bit. So we're talking that aberration is the is some mismatch between some part of the optical system from other parts of the optical system, and a disagreement between where the focal length should be. And so in case of spherical aberration, it's the disagreement between the rays at the edge of the aperture and the rays at the center. The center rays come to focus at one point, and the edge the rays at the edge of the aperture, they come to focus at a different aperture. And this effect is actually quite non-linear in that the as you go more and more towards the edge, the disagreement starts to become more and more. So this thing is definitely non-linear. You can see this effect sometimes very clearly at the if you see this is the tail of the fish, then these are the bones, and you see that the spacing between the bones are getting more and more. So again, this is a non-linear effect, and then it gets non-linearly more difficult to handle as the aperture grows. Okay, so and this is the PSA from the ray trace that we showed in the previous slide, and you see that the PSF is much larger. It's not contained even in a 2 millimeter by 2 millimeter box or 2000 micron, 2 millimeter by 2 millimeter box. Even then, the PSF is spilling over, and this will show you a very defocused image of a star, and you may not see the image at all because the star might be too faint to fill all of this area. So only if you have a very bright star, you will see some light. If it's a faint star, it will just show up as diffuse background. So you will not see the star at all. If you had a good focus and a good PSA, then the even fainter stars will start appearing at your image, because well, they have enough energy to build up this small PSF, but not the much larger PSF. Okay, next we'll talk about chromatic aberration. Chromatic aberration is basically very similar to spherical aberration, except that the parts of the system that are not agreeing with each other are the color input. Let's say we have on the left here we have some charts on different optical materials and how their refractive index changes with wavelength. And you see that yes, most materials they change their wavelength fair bit, they change their refractive index a fair bit when you change the wavelength. And we know from, let's say, an approximate thin lens maker's formula that the focal length is a function of refractive index. It's also function of your radius of curvature, but that is not changing. The refractive index is changing with wavelength. So what happens is that your different wavelengths will come to focus at different points, and then if you want to you can keep your image plane at only one point across this optical axis, and you have to choose a point where the like the spread is minimum. But then again you see that there is no sub place where you can place the optical surface where all the colors are coming into focus at the same time. So this is, well, chromatic aberration, and this comes because the different wavelengths of light have different focal length in an optical system, so you will see chromatic aberration. The simplest way to uh, correct for chromatic aberration is called something, you use an achromatic lens. Basically use two glass materials, one as a positive lens and one as a negative lens, and you hope to cancel out this focal shifts. The positive lens will have a positive shift and the negative lens will have a negative shift. But if you can manage, you can try and manage to cancel out the shift in focus while still retaining some amount of power. If you do it with an achromatic lens, you are mathematically constrained that you will be only be able to bring two different colors into focus. So this is called an achromat. It's doing color correction, but only for 2 points. All other points will have some amount of deviation from this ideal black line. Some of them will have more deviation, some of them will have less deviation, but only 2 points are exactly matching with each other. But this might be too much, this might be too much aberration. So what we can do is we can use an apochromat lens that is typically made with three lens elements, and that will have correction at three different elements, three different wavelengths. So or you can, if this is also not satisfactory to you, you can use more number of lenses. That is why most camera lenses will see a large number of lenses, because they're trying to correct for chromatic aberration as well as other aberrations. And you cannot do it with very low number of lenses. You have to increase the number of lenses in order to correct for all of this aberration. The next is coma. This one also we can explain as an aperture dependent aberration, but this is for off axis rays. So we talked about how a spherical object has a disagreement in focal length. Well, coma is a disagreement in magnification, which follows a disagreement in focal length. Let's say you have a object here and its magnification is dependent on the focal length of the telescope. For different rays that are traveling from different distances from the center, they will come to focus at different points and they will have different magnification. So you will have, let's say, three different images at three different magnifications. And but you can keep your image plane across only one plane. So what you do is you sample one point very nicely, but the other points you will see as rings. Um, one thing I want to keep you as a heads up, that this diagram is very nice, but it's actually in the wrong direction. This one for the particular single lens system is likely to be on the opposite direction. The coma trail is likely to be opposite direction, but again that is fine. We know how to identify coma, because, well, it looks like if you had an ideal point source, the PSF will look like a comet. That's, well, that's the signature of coma aberration. Now we'll talk about astigmatism. It's again something very similar to coma, but this time we have two different planes of rays that do not come to focus at the same plane. So because you have an asymmetry in the system, the one of the plane comes to focus earlier and the other plane comes to focus later. The characteristics of astigmatism is that your PSF now looks like a line instead of a point. um, Often than not, you will not have only one aberration. You are likely to have multiple aberrations and you are likely to see a more complex PSF. And but you have to looking at the PSF, you have to decide whether the system has astigmatism, coma, or a combination of those, of both of those. And so you can design remedies for it. Usually that is not while observing. It has to be done at manufacturing and testing stage.
Oh, it's maybe background, huh? Something goes on happening.
Was this slide coming?
Yeah, yeah, it was coming.
Okay, then I think
came.
it's just
Yeah.
frozen. Yeah.
Suddenly, sometimes it happens. This is the problem with Windows actually.
Yeah.
Yeah, yeah. Because some background is
Yes,
running.
yes,
Yeah,
yes.
yeah.
Gaurav, is Anwesh talking? We are not being able to hear anything.
Okay. So tell me if something is wrong with yeah. Okay. So hopefully I'm audible now. Next we're talking about astigmatism. It's a aberration where the one of the two symmetrical planes of a lens they do not agree on the same focus. This is also an off-axis aberration, and it the planes are usually called tangential and sagittal planes. But what it finally means is that your PSF, instead of being a nice point, it becomes a line. And usually what you will see is that you will see multiple aberrations together, and then you will see a much more convoluted PSF. And then your job is to try and find out a solution for it, which of course you don't do while observing. You do it at the lens manufacturing alignment, that kind of stage. The final one is a field curvature. Field curvature is basically, instead of all the rays coming to focus on the image plane, they come to focus on a curved surface, and then while on the actual image plane you will get a defocus. And then there is distortion, where it means that you have different magnification at different points of the image plane, so your image looks distorted. You can have either positive or negative distortion. um, that is fine. So but these are like a very brief way of telling you all the aberrations. You are not expected to remember all of this, but you know that these aberrations exist, and it's usually the job of the optical designer. But if you do see these aberrations, you should be able to tell the optical designer that this is what you saw, and then maybe the optical designer or like whoever is let's say realign the optical system to fix it. Okay, so here is a more practical example of a piece of an actual system. I'm actually designing this system. What I've tried to do is this is the full spot diagram of the system, and it's done for a wavelength range from 550 nanometers to 900 nanometers. Anyway, that is the total range of observation for this instrument. And what you see is that for this as let's say the first spot, that is top left, is our central field. And as we go to more and more field of view, so from left to right the field is increasing, and from top to bottom also the field is increasing. So the bottom right one is the one that has the most amount of field of view. And you see that this system is not able to correct for lot of field of view. So well, what I can do is I can claim that this system is not designed to correct for all of this field of view. I can maybe say that this is only designed for the only the second row. The third row is, I will say that the system is not designed for this, and the system specification only goes to the second row. Well, that is one way of doing this, but what I'm saying is that a compromise has to be made. I have not tried, I couldn't make the central spot an exact point, nor could I do it for the edge fields. But what I've tried to do is I've tried to minimize it across the entire field. So that is what you have to do. What you want to do is you want to have a system so that none of the aberrations is particularly dominant. You could have some contribution of each of those aberrations, you cannot avoid it. So what you want is you want small contributions from each of these aberrations, and then the total should not go to a very high level. Okay, so let's talk a little bit about the refractive telescope. The Galilean telescope that I sold it was actually a slight improvement on the Galilean telescope. It actually used both positive lenses, both for the objective as well as the eyepiece. So this one was better because it was easily manufacturable at the time. Nowadays you will not make a telescope like this. What you have to do is you a single lens objective simply will not do. What you have to do is you have to have a multi-lens objective. The simple way to do is it's called an apochromat. We talked about what an apochromat is. It's a it's a combination of three lens elements to minimize chromatic aberration. And you could also have an achromat objective, which it's only two lenses. So let's say in a Petzval objective, it could be only the first two lenses, and the second objective, second lenses are not there. But what you want to show you is that modern lens design is much more complex than what could be done earlier. So you can buy this apochromat objective directly off the shelf. It usually doesn't cost that much either. So you can buy these kind of telescopes for fairly low amount of money, and these are really good telescopes because they have been optimized for, well, what a refractor all does reasonably well. You cannot buy this for very large apertures, but these are fairly well corrected. Okay, so the thing is, most modern telescopes are not made of refractive components because it's difficult to make really large refractive components. So what they usually find applications is in back-end instruments. So instrumentation for a large reflective telescope, the instrumentation part is usually made of refractive components. There are some unique exceptions. That is, one of them is the TESS instrument. It's a exoplanet hunting mission, and the you see the optical chain of this thing, it's made of entirely lenses, and then this red thing that you see here, that is the detector. So it's a fairly complex thing, but again, this was what was needed. So this is the present state of refractive components. They are fairly capable, but just not in very large diameters. If you want large diameters, then you have to go to reflective telescopes. So, but before we can talk about reflective telescopes, we have to talk a little bit about conic curves. So basically, the conic curves are basically important for optics is because they have a very unique property, is that the optical path length is conserved between the two foci of a conic curve. Basically what it means that if you have an object at one of the focus of the conic curve, or the conic surface of revolution, then automatically the image is at the other focus. So we'll talk a little bit. Let's say you have a paraboloid. A paraboloid will have its focus. Its focus is at a point, and let's say we make a telescope where we have an ellipsoid and a paraboloid that share the same focus. What the paraboloid will do is it will take an object at infinity and put it at the focus of the ellipse. What the ellipse will now do is it will take the image from this focus, that is also the focus of the paraboloid, and then it will project it back out to the other focus of the ellipse. The ellipse has a secondary focus, so which where the rays will come, and then this is your final image output. um, the simplest way you understand this is, let's say we have an ellipsoid. It has two focuses. Let's say I want to increase the distances between f and f prime more and more. If I increase the distance between these two so much that the distance becomes infinite, then the shape of that ellipsoid will match that of a paraboloid. So you can think of a paraboloid as a limiting case of the ellipsoid where the distance between the focuses have been stretched to infinity. The same for hyperbola, it does this exact same thing, but instead of a real image, it works with a virtual image. So let's talk the simplest telescope, that is a Newtonian. It doesn't have a secondary optical surface. It's basically a flat. So what it basically does, it takes the object at infinity and puts it at focus. The Newtonian is free from spherical aberration, but it has fair amount of coma. So it works very well for small field of view, but doesn't work very well for large field of view. The second one we'll talk about was the Gregorian. It have a paraboloid primary and an elliptical or ellipsoid secondary. So this one is corrected for both spherical and some amount of coma and astigmatism. So this one you can use for fair bit of field of view, not a very large field of view, but definitely some amount of field of view. So maybe around 10-15 arc minutes or so. You have a different version of the same telescope called the Cassegrain. Instead of a elliptical, you have a hyperboloid secondary, and this is again corrected for fair amount of uh, field. So you can get some amount of field with this kind of arrangement. The advantage of this telescope is that this is now shorter compared to a Gregorian, and this is useful because when you are making bigger telescope or like moderate size telescope, you don't want it to be very long, then the um, mechanical assembly becomes too difficult. Finally, we'll come to the RC telescope. It's called the Ritchie-Chretien telescope. We'll find that this telescope is a very slight modification of the Cassegrain type telescope, where what you do is instead of the hyperboloid paraboloid primary, you have a hyperboloidal primary. But the hyperboloidal surface is actually still remains very close to a paraboloid. Let's say um, if the conic constant of a parabola would be around -1. The hyperboloid that is used in RC telescope, it will have a conic constant somewhere around -1.01 or -1.05, around that type. So it's a hyperboloid, but that is very close to a paraboloid. And you have a secondary that is hyperboloid. So this design is actually a compromise between two different aberrations. So you don't have as good on axis performance, but you have still reasonable on axis performance. But this one is the design that has the most amount of field of view, and as such most modern telescopes, larger telescope, actually use this design. Okay, so since we talked a bit about the complex telescopes, let's talk about how do you go from like a complex telescope, go back to the paraxial model where it is just one lens and it um, focuses an object at infinity to its focus. Well, the thing is, the way you get it is you take the rays that are from a Cassegrain telescope and you extend it backwards till it fills the entire primary aperture. Let's say we had an aperture D and we ray trace this thing back till it meets the entire aperture. Then this entire distance is your focal length, and the diameter is, well, that is still your diameter, because the primary is your major collecting aperture of the telescope. So this one decides the diameter, and the focal length you can calculate like this. So what I also want to illustrate is see how short the total length of this system is compared to if we had to make it out of a lens. So it's actually not uncommon to have a system that is like shorter than, like, say 6, 7, maybe 8 times than the total focal length. And so if you are going to build a mechanical structure, this is going to be much more favorable compared to, let's say, we had to make something this big. Okay, so I think for today I'll stop here. Tomorrow I'll start again a little bit from conic curves, because I think I rushed a little bit on that. But then we'll talk about the different subsystems of the telescope. So we'll introduce them a little bit. The first one is the mount that holds the telescope and then points it to the source of interest and has to hold it steady. Then we'll talk about drives that will how to, let's say, move the telescope from one point to the next telescope next point, and to do tracking so that you match the rotation of earth. And then we'll talk a little bit about instrument, different type of instrument that we can use, filters, filter wheels, then auto guiding systems, maybe a little bit on adaptive optic system. I'm not quite sure if I want to go deeper into that, but what I want to impress you on that, the telescope, it has to have multiple subsystems. If you have a dome, you need dome control, you need, if you have detectors that need cooling, then you need some Peltier cooling or liquid nitrogen cooling or some subsystem like that. Additionally, you need some amount of data logging, data storage, computing, some amount of communication, power backup, weather station. These kind of systems also you will need. And the importance of these systems will vary slightly different on different systems, simply because different observatories will have different operation modes. Let's say we have a manually operated telescope. The weather station may or may not be that important there, because you can always count on the observer to look outside and see if if the weather is bad, they can just close the shutter and protect the telescope. But let's say you have a remote telescope that's operating in a remote area, then the weather station has to do this job, and it has to be fully automated, and then it becomes a crucial and important part of the system. So again, but you do have to have some contribution from this entire system to make it work correctly. Okay, so I will stop here today. If there are some questions, I can take now. Otherwise, what I will do is I'll come back again and we'll talk a little bit more of reflective telescopes and then move on to systems.